Hello, everybody. Welcome to physics, either pre-ACE or ACE physics. We'll start out by looking at the physics of kinematics. And so in this video, I'm going to go over all the learning objectives associated with kinematics. I'll upload additional videos to support some of the learning outcomes that are more relevant to sort of doing worked example problems. You'll see in a moment. So I like that better instead of chapter 1. Let's call it kinematics. Hold on, let me jump back in here. All right, so kinematics for both pre-ACE and ACE physics. ACE physics, we're going to sort of go at a slightly faster pace, but sort of covering the same things. If you took pre-ACE physics and now you're in ACE physics, then you have a tremendous advantage of having basically gone through a majority of the course already. So hopefully, you might still have your physics journal from pre-ACE, keep that handy. The physics hasn't changed much, in terms of kinematics for the last, 400 years or so. Please keep a record of all of your work in a physics journal. You're going to send me photographs or scanned copies of your journal pages to my email, schleith.david@brevardschools.org by noon, Friday each week. All right, here are the learning outcomes. We're going to define displacement, speed, and velocity, draw and interpret displacement time graphs, describe laboratory methods for determining speed, and then use vector addition to add 2 or more vectors. Every learning outcome has a corresponding essential question. These are ones that I sort of thought of, but you get the idea. You want to try to turn every learning outcome into an essential question that you're going to answer where in your journal, because that's where you keep a record of all of your work. So say like, what am I going to do in my journal? Whatever you have to do to master those learning objectives. I recommend, having like some pages dedicated to vocabulary, some pages just to practice problems, to taking notes from my lectures, or as I go through worked examples, things I say, oh, here's something noteworthy. We'll read articles, we'll do experiments, so your data tables are going to be in there. Basically, everything we do needs to be in that physics journal. And like I said, that's what I'm going to grade. So every week you'll just send me, pictures of all the work that you're doing there in that journal. You can also keep like an electronic record. So if you prefer to, type it all up, but I prefer that you have a handwritten, copy to send to me. You can also send me your, your digital copies there, but I will require you to keep a handwritten copy as well. How can I define displacement, speed, and velocity? How do I draw and interpret displacement time graphs? Why is it important to describe laboratory methods for determining speed? And how do I use vector addition to add 2 or more vectors? It's really up to you how you want to organize your journal. So you might have a page with all the essential questions which belong to kinematics, and then you sort of break them down, you deal with sort of one at a time, or maybe you go back to that page and sort of add in answers to it. My suggestion is that you just sort of keep a chronological record of your work. So whatever you're working on, today, put the date by it. So here's all my notes from today, and I'll give you all a lot of freedom to kind of use your time as you see fit. As long as you're working towards those learning objectives. All right, define displacement, speed, and velocity. Let's just jump right into it here. So displacement, that's a vector quantity, and it's defined as a change in position, and we measure it in meters. And so there's a lot sort of embedded within this definition. We haven't really talked about what it means to be a vector versus a scalar. So that's a really big idea that's going to remain with us throughout the course, and we'll sort of deal with it explicitly in its own right, in a subsequent video. But for now, we're just going to sort of keep in mind that there are quantities, physical quantities, which sort of is another big idea, and those physical quantities may be either vector or scalar in nature. Vector just means that the quantity tells us how much and which way. So it has both a magnitude and a direction associated with it. Scalar quantities have just that magnitude only. They just tell us how much of something. There's really no direction associated with it. So we'll spend a lot of time throughout the year sort of dealing with that idea. But for now, we know that displacement, it's a vector, so it has direction. You can kind of see this vector here going from point A to point B. That would be the displacement vector there. You can see it's got a direction sort of above, east here, sort of going, northeast, closer to the east than the north though. And, it's moved, we could calculate how far this moved. It looks like it went 5, units to the east and then 1 unit north. And so we could calculate what the magnitude of that is, and we could even calculate, the angle sort of above due east, how far north of east is this displacement vector. And we'll spend a lot of time doing those sorts of calculations. There's a difference between distance, which is a scalar quantity, and displacement, which is this vector quantity. So it seems like, we could kind of imagine with this graph down here, a person traveling from point A to point B, but walking along sort of the blue path there. In other words, they went one, let's call these blocks, okay? They went one city block east, and then they went one block north, and then another block east, and then 2 blocks north, 1 block east. They went back, south again for a block, and then east a block, back south another block, and then 1 more block east, and they ended up sort of here. But what's the total sort of displacement? So it's the net change in position is another sort of good way to think about displacement. It's just the overall change in position. We don't really care about the path traveled. We're just interested in a starting point and an ending point, and sort of how much space is between them. And so in ACE physics, we use the letter S for displacement. Every time we're, say, calculating displacement, we don't want to have to write out displacement every time. There's a lot of letters in that word. So we just use S, and it sort of comes from the Latin for spatium, the space between 2 points, you could think of it. And, what's the distance and direction? That would be displacement. Distance by itself is a scalar quantity, and, we could sort of, let's just add it up real quick. What is the total distance traveled here? Well, 1 block here, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 blocks, that were traveled total distance, the path, the blue line path there. But we can kind of just sort of eyeball the numbers there and say, well, the person really only traveled a little bit more than 5 blocks. Maybe there were buildings in the way or something obstructed their path, but they could have just walked, 5 blocks east and then 1 block north and been at the same place, or they could have just, flown from path A to path B. Oftentimes that straight line path is called the crow's path, because a bird can just kind of fly from any points. They don't have to worry about the obstructions that may hinder us moving here on the ground. We would use, some of you may have already sort of anticipated, Pythagoras' theorem to calculate what the magnitude of that vector is, because we sort of can construct a right triangle there with legs, 5 units and 1 unit. And so, 5 squared plus 1 squared would be, 26? And so that would be the square root of 26. Would be the magnitude of that, somewhere like 5.1 or something like that. Calculator check. You all should have a calculator at all times. Let's calculate it real quick. I got one here. Of course. So what I say, root 26. So what's the square root of 26? 5.09. I would say 5.1. So yeah, I'm about five blocks here. A little bit more, right? A little bit more. Anyway, so that's displacement. We'll spend a lot more time with this idea, sort of an introduction. Make sure you have that definition down in your notes, maybe a blank page. Some practice problems we'll do with displacement vectors. Maybe you sketch this figure. For those of you, taking some time with this video after class time, maybe now's the time to pause the video and go look at some other, videos related to displacement, or, feel free to learn as you see fit. Here's an example, a figure that kind of shows the same idea, where maybe the actual path traveled is, it tells us here, is this blue sort of line here. And so the distance is sort of sketched out in purple above it. That's the actual distance, the scalar quantity, the total sort of, distance traveled. But the displacement is just that difference, that net change in position. So from this point to that point, we can see the displacement vector is sort of sketched out and with this green dashed arrow here. So this slide is highlighting the difference between this distance, the scalar quantity, the magnitude only, and displacement. Note that displacement tends to be less than the distance traveled. Usually the path taken is longer than the displacement. Unless you travel, along this path, then the distance is going to always be, greater than the displacement. Unless you're very clever and you can think of ways where perhaps, how could we be further away than we've actually traveled? Could our displacement ever be greater than our distance traveled? If you're pretty creative and willing to introduce, some sci-fi-ish themes in, then perhaps you could be clever enough to come up with some ways. If you can, leave it down in the comments below. All right. Now we've moved on to speed. So speed is actually a scalar quantity. So all we care about is how fast something is moving. That's sort of what speed is. It's the distance traveled divided by the time taken. We measure it in the SI units, meters per second. And we'll get more familiar with, comfortable with meters per second as units for speed, and also velocity. Velocity is just the vector sort of version of speed. So once we kind of know the direction, that's what velocity is. So speed is just the scalar quantity. The total distance traveled divided by the total time taken for whatever sort of part of the motion we're considering. Very similar definition for velocity, although the nuance sort of different is an important one here, that velocity is, as I mentioned, that vector quantity, and it's defined as displacement divided by time. So displacement itself is a vector. When you divide it by time, you get velocity, the vector. Distance, which is a scalar divided by time, you may have noted was how we get the scalar quantity speed. So we can kind of see corresponding vector scalar sort of combinations here. Displacement is to velocity as distance is to speed. Displacement and velocity are the vectors. Distance and speed are the scalar quantities that we've sort of talked about. And again, every quantity we're going to look at this year is going to either be a scalar quantity or a vector quantity. And the difference is just, does it have direction? If it does have direction, if the direction of the quantity is given or calculable, if it has a direction associated with it, then it's a vector quantity. And velocity is an example of a vector quantity. A displacement time graph is a way to sort of graphically represent an object's motion, or a particle's motion, or a collection of particles sort of motion, where we typically put time on the x-axis against the displacement on the y-axis. And so if I were to just sort of kind of walk through this, we could see something that starts out at a displacement of 0, and then after 5 seconds it's moved 5 meters, and so it's moved 1 meter every second. You can kind of follow that. Indeed, the slope of this line is the velocity, right? Because it's telling us the rate at which an object is changing its displacement. And so the rate of change of displacement is velocity. Displacement divided by time, another way to sort of think about this definition here, is the rate of change of displacement. Velocity is the rate of change of displacement because it's happening sort of as a function of time. So here it's changing its displacement at a rate of 1 meter per second. So after 5 seconds, it's traveled 5 meters. Then it just sort of, the slope goes to 0. We can just sort of see graphically it stays here at 5 meters for another 5 seconds. And then it goes back to where it started, returning to the original displacement of 0, but does it a little bit more quickly. It's able to get there in about 2.5 seconds. And so that's the way we would sort of interpret this entire displacement time graph. Something moved 5 meters away, it stayed there for 5 seconds, then it went back to where it started after 2.5 seconds. Maybe it saw something, scared and it ran back. You could make up a sort of a clever story to go along with this if you wanted to. Be mindful of, what's reasonable in terms of, how far away actually is 5 meters. Typically, unless maybe you've taken, pre-ACE, or maybe you're from a place around the world where they use the metric system more often, we typically are not too familiar with how big 5 meters actually is. If you're in the classroom, these lab benches across here are about 7 meters long, so a little bit less than one of these entire sort of lab benches here. Draw and interpret displacement time graphs. The same learning outcome is just a different sort of plot here. And so here we can see something that travels, from its original position 0, and it goes like 4 meters away after 5 seconds. And again, the slope there would give us the velocity. Then it sort of turns around, it goes back through where it started to some negative displacement. We just interpret this, sort of negative with, the sign convention that we sort of adopt in physics is that this is the opposite direction. And so something that sort of moved, let's say, to the right, and turned around and moved back to where it started, and then continued moving, towards the left. And so left would be negative, right would be positive, or, up could be positive and down is negative. The sign convention that the physicists adopt is really up to them, sort of what's convenient. I prefer to, if you're sort of given the choice, And usually you are, at least at the beginning of the calculation. You say, well, I'll just call, the direction of motion positive. If I can anticipate the direction that something's going to move, I want to make that the positive direction. Here we see that, something is moving sort of in both directions here. And so that's how we deal with that mathematically, is adopting what we call a sign convention. So something went, sort of back through where it started at about, 7.5 seconds maybe, and then it went to -4 meters away after 10 total seconds, and then it just sort of stays there. And that's the plot of its motion. Again, you can see here they're using s, that variable s, for displacement. This m in parentheses means they're measuring it in meters. Time, t, measured in seconds on the x-axis. That's a displacement time graph. If you want to, in your journal, you can create your own displacement time graphs and sort of come up with a cool story that goes along with it. I'll show you one in class, maybe right now. If you're sort of watching this, you could, ask a question, pause the video, say, hey, can you show us a cool displacement time graph? Help with that sort of learning objective. Lots of good information on this slide, again, belonging to the learning outcome: draw and interpret displacement time graphs. So we have a displacement time graph, and the plot looks sort of a little bit more complicated than we've seen previously. We're still plotting displacement against time, and so the slopes here give us velocity, but we see we have a changing slope. And so here the slope is changing. Like if we were to just sort of draw a line tangent to any point here on this curve, we would see that the slope is increasing, right? It starts out with a shallower slope, and then it gets a little bit steeper right here. I can use a drawing tool here, right? And so here we can kind of see like the slope starts out very shallow, but then by like this time it's gotten very steep. So it's changing its slope. Well, if the slope is velocity and it's changing its slope, it's changing its velocity, that's acceleration. When things change their velocity, that's acceleration. And we're going to deal with acceleration in its own right. It's actually, the subject of sort of the next big idea, which we'll get to maybe in a week or two. Here we see this constant slope, and that means constant velocity, right? And so this is something that's moving at a constant speed, a constant velocity. And then here we see that it's changing its slope again, right? It went from steep, and now it's becoming more shallow as time goes on. And so this would be an example of deceleration, right? It's decreasing its velocity, and so it's still changing its velocity, but now it's slowing down, and so decelerating. And then here the slope eventually just sort of goes to flat, and again, a slope of 0 means there is no rate of change of displacement. The rate of change of displacement is 0, and so the velocity is 0 at this point. And you can just kind of make sense graphically. Okay, as a function of time, it's just sort of staying at this displacement. So it's like it's sped up, stayed at this speed, it slowed down until it stopped, and now it's just stopped. And this total displacement away from where it started. There's no numbers on this scale, but we could call it maybe 5 meters, like the last one. So the gradient of the displacement time graph is velocity. That's a very noteworthy sort of statement there, right? That's going to be very helpful to us if we're given graphical sort of information, data. We could, maybe calculate what the velocities are by looking at slopes. If the graph goes up as a straight line, the velocity is constant, right? So the slope isn't changing, so it's a constant velocity. The area underneath this graph has no meaning. Sometimes in physics we'll be able to take the area underneath a curve, and that will have some meaning in the universe. But the area underneath the displacement time graph, like if we were to multiply displacement by time, we'd have sort of there's no physical meaning of that, like space-time. Space-time is a thing in physics, but we're not getting that by taking the area underneath this curve. So one of the learning outcomes was to describe laboratory methods for determining speed. So speed is distance divided by time. To measure distance, you need like a tape measure or a ruler or something. To measure time, you need a stopwatch, some way to keep time, and you need to record those things. So really the only way to determine speed is by, measuring distance, measuring time, and then taking their ratio, dividing the two. If you wanted to, describe laboratory methods for determining velocity, it's very similar. You measure the displacement, so the net change in position, using the same tools, tape measures, rulers. some way to get the distance, the displacement, and then a stopwatch to measure the time. So displacement divided by time is velocity, as we mentioned earlier, and distance divided by time is speed. You should conduct a lab sort of on your own this week and keep a record of it in your journal. It's up to you to kind of design your lab, measure the speed or the velocity of something. You pick, you kind of set up the lab yourself with very minimal guidance from me. It's okay to ask me a question. How do you want us to do this? But try to be creative and, you could measure the speed of like an ant, if you're like outside and you see like an ant moving, you could lay a ruler down or, I don't know. I don't want to give you much more guidance than that. Just, measure the speed of something by measuring the distance it travels and the time it takes to, travel that distance and then divide the two of them. So distance divided by time, right? That's speed. So do that lab this week. Lab day is usually Wednesday, but we'll have some flexibility, especially this year. All right, use vector addition to add two or more vectors. We already kind of mentioned Pythagoras' theorem, and so the easiest thing to do in terms of vector addition is to just add vectors that are in the same direction. Like if two vectors went due north, if I had another 11-kilometer north vector that I added to this one, you guessed it, I'd be 22, kilometers north. So we can add vectors in the same direction just by, summing them. If vectors go in different directions, then we do have to be mindful of direction, to get the sum or the resultant. That's what this R here is for. To get the resultant, the sum of these, we have to be mindful of the direction also. And so we'll employ, a fair amount of trigonometry. I'll sort of give you a crash course in a little bit of trigonometry that will be helpful for physics, but it'd be very important to study not just trigonometry, but sort of more advanced mathematics to help you become a more competent physicist, which is a sort of overarching goal in this class. So I'll tell you that you'll have, sort of the freedom in your assignments. Well, let's just take some time to talk about it now. Whether you're, an e-learner, you're an in-class learner, once you've kind of gone through the learning outcomes and you kind of know what your job is, okay, I'm expected to sort of master these learning outcomes, feel free to have some autonomy, some freedom in how you want to sort of attack those learning outcomes. Those essential questions, see how they're worded. How can I, learn this? How can I do this? And people learn differently. And so you might say, well, I decided to watch, a YouTube video. I'll give you a list of sort of approved YouTube channels that may not be directly related to the physics we're looking at, but, really good sort of math videos that will pique your interest, maybe spark some curiosity and get you thinking sort of along sort of the universe and, along mathematical lines. So some of those off the top of my head are Mathologer, 3 Blue, 1 Brown, Physics Girl, Walter Lewin's physics lectures. I'll give you a list, and you all might have really good suggestions too. Then you'll say, oh, this is a YouTube channel that I watch, and it's very informative and educational, and would I be able to sort of review videos as part of my work? And again, sometimes you might use that assignment as just a break from your brain starts turning to mush as you're going through, example problems related to some of these learning outcomes. And I say, oh, I just need to, sort of let my mind sort of wander a bit and then come back to it. There's actually a lot of science of learning that's a great way to learn, actually, to sort of take a mental break sometimes when we're sort of feel bogged down. So you will have the freedom to kind of take a look at some other assignments that will help you become a more competent physicist, even though it may not be directly related to these learning outcomes. But you can find a wealth of material that are specifically related to this beyond just sort of this YouTube channel, so feel free to explore. And just do your job to learn, feel like you're learning this and ask questions. And the ultimate test will be, can you sit for the ACE papers and demonstrate your mastery by answering those questions successfully. So here we see they've added an 11-kilometer north vector to an 11-kilometer east vector, and they've just used Pythagoras' theorem to do that, and they've got the magnitude of this vector, so 15.6. A few things wrong with this calculation is that while numerically it's correct, they've dropped the units here. We always want to report, if kilometers go into the calculation, then kilometers are coming out. So it's 15.6 kilometers would be the magnitude of this vector R here, the resultant. If we're adding two vectors, we typically want to report a vector answer. So this vector is neither due north nor due east, but sort of northeast. Well, how far east of due north is it? That would be sort of a calculation of this angle right here. And here we would use the trig functions to calculate that angle. Because we know the values of sort of every side of this right triangle, it's a right triangle because due east relative to due north is a 90-degree angle, we could use any trig function to calculate sort of this angle theta right here. Remember that the trig functions relate the sides of a right triangle. That's one of the things the trig functions do, I should say. And so if we already know the side opposite this angle and the side adjacent to this angle, then the tangent function is a useful function in sort of solving for the angle there. And so the tangent of that angle is this ratio, 11 divided by 11, or 1. So if we want to solve for the angle itself, we would use the inverse tangent function. So the inverse tangent of 1, or the opposite over the adjacent, 11 kilometers divided by 11 kilometers, would give us the angle. I'm pretty sure that's going to be 45 degrees. Because if it goes 11 up and 11 over, it's going to perfectly bisect that 90 degree. We may just have it sort of memorized. Yeah. 45 degrees. So we'd say 15.6 kilometers, 45 degrees east of north, would be a way to report the direction of that vector also. And we'll have a lot more practice with those sorts of worked examples, as the week and year goes on. So at 90-degree angles, we can use Pythagoras' theorem, but sometimes we have to add vectors that are kind of like this, like, they're not perfectly aligned with the x and y axes. So what if we had a vector like A here, a vector like B here? How could we calculate the resultant? So here, there are different ways to sort of go about solving this. Students that have already taken a fair amount of math may, think about like the law of sines or something like that right now, which, depending on what information you're given, that may be the most straightforward path to the solution there. And so feel free to, if you see a way to solve it, go for it. And then always you can kind of check your answers by using some other method. Resolving a vector is a way to take a vector and sort of break it down into its x and y components. And so if I look at sort of vector A here, I could break it down into its horizontal and vertical components. We could adopt a convention like, I'll call this vector here that's horizontal the x, A sub x, the x component of vector A. And similarly, this vector here would be the y component of vector A. B also has x and y components. You can see B brings you so far over, it brings you a little bit more up. And so there are y components of vector B and x components of vector B. Vector B is that blue one, vector A is that red one there. So one of the ways to add, two or more vectors that either aren't pointing in the same or opposite directions, where we just add or subtract them, or they're not perfectly at right angles to each other, so we can't use Pythagoras' theorem. But we can always resolve a vector, hopefully, by breaking it down into its x and y components. And if you're given the vector information, in other words, if you know how long that vector is, that's like the hypotenuse for a displacement vector, how long it is. If you know how fast it is, that's the magnitude of the velocity vector. We can resolve any vector in physics, and we will throughout the year, which is, again, just breaking it down to its x and y components. So we can take a vector that is the hypotenuse, okay, and if we know its angle also, then that's all the vector information. We know its magnitude, we know its direction, and we should be able to use trigonometry to sort of resolve that vector, to break it down to its x and y components. And then to solve for the resultant here, this vector that's drawn in black, we would simply add up the x component of A, which brings us over about this far, right? And then we'd add that to the x component of B, which brought us over. I didn't line that up exactly perfectly. You get the idea. Then AX plus BX is Rx. So the resultant x component is simply the sum of the x components of the individual vectors that we're adding. So Rx is Ax plus Bx. And again, the way that we calculate the values of Ax and Bx is by sort of using the same trigonometry, that we looked at in the previous question. If we knew the values of these angles here, let's call it theta 1 and theta 2 or something. If we knew those and we knew, the magnitude of these, let's call them displacement vectors, then we would easily be able to resolve it, once we're comfortable with our trig, and then we'd calculate the resultant just by summing those x and y components respectively. And so the y component of vector A brought us up about this much, and then the y component of vector B brought us up sort of the rest of the way this way. Once we've summed the y component of vector A and the y component of vector B, we'll have the resultant y component. We can call that r sub y. And once we know the x component of vector r and the y component of vector r, we simply use Pythagoras' theorem to find the resultant of the entire vector. I know there's going to be a lot of questions about this, and we'll spend a lot of time working, especially with worked examples on this one. And so bring those questions to class. These are the learning outcomes just for the very first idea, which is kinematics. Please don't hesitate to reach out if you guys have any questions about anything. Just keep a record of everything you're doing in your journal there. And I'm more than happy to work with you to try to help you achieve that overarching goal, which is to become an ever more competent physicist. See you guys next time.